So then let's recap the 4 steps we just described here. So we're starting with original image on the left, and then we identify the edges or the boundary contours, where the higher the PB value, the darker the contour. So we can see already we have regions that are clearly identified. So we can segment these into regions corresponding to a fine partition of the image. And then regions are rendered in their mean color. So we just get the average color for each region and give that average to all the pixels within a given region. And then we do then new segmentations of each region into new regions corresponding to a finer partition of the image, resulting in even fewer regions. So let's look at some applications of computer vision. So first, classifying images. So modern systems classify images using appearance, color, and texture, as opposed to geometry. So there are two difficulties then. Different instances of the same class could look different. So how can the network tell, for example, that a black cat and an orange cat are both cats if they have two different colors? And then they might also look different at different times of the day. Okay, so for example, depending on the lighting, the aspect, the foreshortening, all of these elements that we discussed earlier, the same cat can look different in different images. The model still has to, or the neural network still has to be able to identify that it's a cat. So to deal with these problems by learning the representations and classifiers from a very large quantities of training data using what's called convolutional neural network. So the solution is then to get thousands of images of cats from all colors and from different time of day, different lighting, and so on, and then train a network that all of these contain a cat. Then hopefully the network will be able then to identify that or classify an image as an image of a cat when given a new image. So with enough training data, convolutional neural networks then produce very successful classification systems. Images can have small variations without changing the identity, so the network will still be able to say that this is a cat. Local patterns can be useful as well for the network, and spatial relations between local patterns are also informative. So convolution followed by a ReLU activation function. This is typically the process we use here in classifying images. Is used as a local pattern detector. So convolution measures how much each local window of the image looks like the kernel pattern. And then ReLU sets low scoring windows to 0 and emphasizes high scoring windows. When we do convolution with multiple kernels, then we can find multiple patterns in the image. Okay, so we can split the image into different kernels. One kernel can find a cat in the image, another one can maybe find a plant in the image, another one can find a toy, and so on. So composite patterns can be detected by applying another layer to the output of the first layer. Now we can also apply dataset augmentation, where training examples are copied and modified slightly. So let's say we only have a few photos of cats, then we can maybe generate some slightly modified photos and use them in training as well. So maybe we can flip the cat, for example, around an axis to generate a mirror image of the cat. The network can still be trained on this to identify that it's a cat. Maybe you can change the pixel intensity a little bit to make it blurry. It still contains a cat. Maybe we can randomly delete some pixels completely, just sets intensity to 0, and so on. So this is called dataset augmentation by essentially doing random shifts, rotation, stretches on an image by a small amount, okay? Or randomly shift the hue of the pixels by a small amount, again, changing the colors and so on. So all of this will allow us to take that initial 100 training record and maybe create 10 times more training records. So CNN-based classifiers are good at ignoring patterns that aren't discriminative. Okay, so if it is really can tell us whether or not it has a cat in it, the network will not even pay attention to that part of the image. Now, as far as context, patterns that lie off the object might be discriminative, so it depends really. For example, a cat toy, a collar with a little bell, or a dish of cat food might actually help the network tell that we're looking at a cat. Okay, so if even if it's unable to see the cat directly in the image, it can still get clues from the context of in the image. Now, detecting objects. So object detectors find multiple objects in an image. Okay, so they report what class each object is, and also report where that object is given a box around the object. So, for example, when you consider self-driving car, when it looks at an image, it's going to create a bunch of boxes in the image, and then it's going to give you the probability that each box contains a specific object, whether it's a red light, it's a pedestrian, it's a car, it's whatever it is, it can identify in each box. So building an object detector then involves looking at a small sliding window onto the larger image. Okay, so we have this window that's gonna sweep over the image, and then at each spot, the window is gonna try to classify what it's seeing within that specific spot using the CNN classifier. Now, when you actually implement this in practice, how large does the window has to be? It can't be a fixed size window because, for example, a red light has a different shape than a pedestrian. So deciding on a window shape, is it a vertical window? Is it a horizontal window? That's important. Again, and the window has to be able to extend in any direction to capture more of a given object. Then build the classifier for the windows. That's the second implementation step. Now decide which window to look at, choose which windows to report, and finally report precise location of objects using these windows. So then we have to be able to get an output that says at for a window that has a lower left-hand corner at x0, y0 and an upper right-hand corner at x1, y1, I detected a red light. Okay, so it has to report the location and it has to report what's inside the window. So a network that finds regions with objects is called the regional proposal network, RPN. Okay, so faster RCNN encodes a larger collection of bounding boxes as a map of fixed size. So if we don't change the size of the window, it can be faster, but it's not going to be as accurate as the variable or the region-based object detection. So we're going to construct this 3D block where each spatial location in the block has 2 dimensions for the center point and 1 dimension for the type of box. Any box with a good enough objectness score is called a region of interest. Okay, so if you find a high enough probability for what's inside the box, and then we make them have the same number of features by sampling the pixels to extract features, which is called ROI pooling. So a greedy algorithm will be used then for deciding windows to report called non-maximum suppression. Okay. So here's an image. So first the network computes the objectness score score of a candidate image box. So you can see that it's recognized that the blue box has the highest score here. It will be called anchor boxes. And then the second network is a feature stack that computes a representation of the image suitable for classification. Now, if we're looking at this 3D world, then we need two pictures of objects because that's much better, more information than one picture. So two images of the same scene taken from different viewpoints, and you know enough about the two cameras. So you get two views of enough points, and you know which point in the first view corresponds to which point in the second view. And then the key problem then is to establish which point in the first view corresponds to the second view. Okay. So to get multiple views of a scene, we can have two cameras. So obviously, again, if we go back to the self-driving car, the self-driving car looks at the same object from different cameras. And then by using the classification from each one of them, it's able to determine exactly what it's looking at. So here's an example. So translating the camera pair to the image plane causes image features to move in the camera plane. The disparity in position that results is acute to depth. If we superimpose left and right images, we can see the disparity. So some usage of computer vision. First, understanding what people are doing. So the difficulty here is how to link observation of the body and the objects nearby to the goals and intention of the moving people. Another difficulty is caused by the time scale. So what someone is doing depends on the time scale. Is he moving fast? Is he moving slow? And then there might be unrelated behaviors that are going on at the same time. So learned classifiers are guaranteed to behave well only if the training and test data come from the same distribution. So, which means that if you train your computer vision network, say, in a cloudy environment only, and then take that network and try to do object recognition in a sunny environment, it's not going to work well because your training data came from one distribution, which is mostly cloudy, with specific intensity distributions for the pixels, but your test data or your production data is coming from a totally different distribution. So for activity data, the relationship between training and test data is more untrustworthy. People do so many things in so many contexts, so it becomes even harder. For example, here this shows reconstructing humans from a single image is now possible. Each row shows a reconstruction of a 3D body shape using a single image. So we feed the network one image, and the network is able to come up with a 3D model for what's in the image. More examples of computer vision applications. So the book discusses a lot of applications. I recommend that you go over them to see all the places where we use these convolutional neural networks now. And hopefully this was a useful lecture for you, and I'll see you in the next lecture.